Now to the statistics part. The confidence intervals, 1 and 2 samples. So now we do this part. We started out with one sample, just one column in the data set. And then we were going to learn the concept of confidence intervals. That's the first thing we did from a statistical point of view. The idea, and we saw the formula. Do we remember the formula here? X bar plus minus a t quantile times the sample standard deviation over root n, if I remember correctly. The t then depends on the alpha and the number of observations. We use n-1 degrees of freedom, right? But so basically it's the average, the mean, plus minus twice the uncertainty of the mean, the standard error of the mean, the sampling error of the mean, the sampling standard deviation, the standard deviation of the sampling distribution of the mean. I just said the same thing 5 times in a row now, with slightly different words. This one coming from the variance rule that I just shared with you a minute ago, right? A confidence interval is a tool which in 95, if we use the standard 95% confidence interval, that is a tool that from time to time it will include the true value, that is the true mean. In this case, it's a confidence interval for the mean mu in 95% of all cases. That's the classical long-term frequentist interpretation of a confidence interval. The other interpretation, which I favor a lot and like a lot, is to say the confidence interval. That is, in a way, combining it a little bit with the hypothesis testing idea, saying, that comes in a minute, the confidence interval are those possible values for the true mean that I accept or that I could believe in, given the data information that I have. Those outside the confidence intervals, those are the possible values for the truth that I don't believe in, right? So I make this distinction between the likely values and the unlikely values. That's goddamn intelligent, right? That's a good tool. We distinguish between population and random sample. We do the data. We see that as a random sample from the population, the real life, the future, whatever the population is. It can be rather abstract sometimes, but nevertheless, that's the whole statistical inference idea. When we compute the confidence interval, we use the data to say something about the real life setting that we're positioned in, right? That is statistical inference. That is what all the tools in this course is about. To do that, we need the probability. That's the thing. We need the probability to do it intelligently. And this one here comes from probability, because probability tells us that the t-distribution is the right sampling distribution. So when I compute a mean, the way a mean, at least if I standardize the mean by the standard error, the way that one will change from sample to sample is like a t-distribution. So here's a theory that tells us what should be your measuring stick to use the data information. How should I learn from this information, which is the mean? Well, someone told you the way to be intelligent here is by thinking in terms of a t-distribution. The t-distribution is the intelligence filter here, right? So when I look at the mean, I should remember the t-distribution to know about how good is this mean for me, right? How close to the truth is this mean? Well, the t-distribution is the one that can help you. It's a random thing, so you cannot just give a number answer saying, I am far away from the truth. That's not intelligent. That's not how life works. It's a random thing. So you have to control the randomness by knowing the probabilities. People found the t-distribution for you, so the t-distribution helps you controlling the value of the mean when you use it, right? Think about how many means you already used in your life and how many means you're going to use the rest of your life. If you want a better life, remember the t-distribution. We also saw this central limit theorem. The central limit theorem made the normal distribution very central to us, because that's a quite amazing result, that means tend to behave like a normal distribution, no matter what the original data distribution actually was. The thing is, the t-distribution theoretically comes as a consequence of a normal assumption, right? That you assume, that's the classical assumption in stats, that you assume that your original distribution is a normal one, then you can extract the t-distribution from probability theoretical results. However, the central limit theorem tells us, maybe it's not too bad as long as the sample size is big enough, we can still use normal-based methods, because the mean behaves like a normal, more or less, from time to time. That's pretty strong. So we saw confidence interval for mean and variance. The mean was the t-distribution, the variance was the chi-square distribution. And then we could also see that we could turn the confidence interval for the mean around and find some kind of formula for the n. I'm not giving you the formula, it looks something like that, with the wanted margin of error and then the percentile, quantile of the normal distribution. It's an approximation, and then you can find out what would the needed sample size be to achieve the right confidence interval width. Then we turn to hypothesis testing, the other big tool. There are two big tools here, the confidence interval tool, the hypothesis testing tool. We learned about that we can hypothesize something about a mean, typically that it has some given value. We can test that hypothesis by computing a test statistic that measures the difference between the hypothesis and the data, right? I put up a hypothesis, I use my data to evaluate whether I'm far away from the hypothesis or not. If my data is far away from the hypothesis, I don't believe the hypothesis. If my data is close to the hypothesis, I believe the hypothesis. That's quite a naive approach. It's intuitively straightforward. It's only all the practical things. How do we do it then? Well, it's also really based on probability. We saw the t-test for a mean, classical t-test, where we compare the mean by the hypothesized value and we divide again by the standard error, and we get the classical t-test for a hypothesized value of the mean. We saw that we would reject if such a t-test statistic becomes too large. We reject. If it's two-sided, we reject out there, and if it's not large, that is, if our data and hypothesis is close to each other, we accept. If they're far away, we would reject. We have to think about this one-sided, two-sided thing. Sometimes it's both tails, other times it's only one-sided. It's a little extra annoyance here, but the principle is the same. There's just those two different versions of it. We also saw that usually we put the significance level at 5%. That's the globally chosen 1 out of 20 type 1 error rate that people have decided that we are going to live with all the interesting consequences that has. That 1 out of 20 cases where nothing is to be found, people think they find something. And if you think about how many studies is being carried out around the world all the time, then there are a lot of false positives here. But anyway, there is a price, because then why do we have to live with such a high risk of claiming that we found something? Because this 5%, that is the probability that we go into the extremes even though nothing is there. So we get a signal in our data, even though there shouldn't have been, even though the truth is there is nothing. Why don't we just turn it down then? Why do we want to accept to live with a 5% error, type 1 error rate here? Well, it's because there are no free lunches. Because if we turn down the type 1 error rate, the alpha, we will turn up the beta, right? the type 2 error rate, because if we want to be very strict before we claim we found something, it means we very often will say we didn't find anything. And then there is a risk we commit the other error, that we say we didn't find anything even though we should have found it, right? So if we want to be more critical before we said we found something, then we will make more type 2 errors where we don't find something we should have found. So it's a trade-off. None of them can be zero if we want to move forward in life. We have to live with a certain level of both. And we decided to live typically with 5%. Sometimes we talk about 1%. Sometimes we talk about 1 per mil. These are the default codings of R in regression, for instance, right? They talk about, and also ANOVA tables. 1 star, 2 star, 3 stars. 1 star means below 5%. 2 stars means below 1%. 3 stars means below 1 per mil. And these are the different evidence levels we've also shared with you in a table. That if we have below 1% of a p-value, the p-value measuring was the probability to go beyond the observed statistic. If that is below 1%, we have really strong evidence. If it's below only 5% in a way, we have some evidence. That's the way we interpret it. And then we could also turn this around slightly more intelligently than we did before with the confidence interval. We can be precise about the beta and the power. Power is 1 minus beta. Power is the probability to detect an effect if it's there to be detected. So it's a scenario-based tool that we can say, what if my treatment group of this cancer treatment has a 10% higher survival probability than the other group? Will my experiment that I planned with 1,000 patients, will that likely detect that improvement if I do that experiment, if I spend a few million investigating this cancer treatment? Will I find this improvement if that's what is to be found? It's a scenario-based thinking. If I get the power out saying there is only 50% chance you're going to find that effect with the money you have, I should spend the money otherwise. I should use the money for some different. I should either not do it or I should spend more money. To do it in the middle is a waste of money. And then we also learned that we could compare observed data with the normal distribution by probability plotting. Then we went to 2-sample statistics. Comparing 2 means. Doing the same thing now. Hypothesis test and confidence intervals. Still based on the t-distribution primarily. And we could also do this power thing. Power usually by most people, and understandable so, is considered complicated. It is a pretty complex issue. There are many things in place, but please go check that you have some in R. We did this in a way very R-oriented. There are some power functions in R that we can use and that you should be able to use, right? Go check that. And then we could have either paired or independent samples when we have the 2 columns, right? Either it's different people or different whatever units in the different groups. That's the independent samples. That's the 2-sample t-test. Or it's paired design where, for instance, the same persons had the same sleeping medicine before. I mean, sleeping medicine A and B. That's the example we saw in the notes. And then we take the differences, and in a way, it's just a 1-sample thing. So that's a distinction with 2 samples. It may be independent or it may be pair dependent, right? You have to think about that. All of this was based on normal distribution assumptions or hoping that CLT, central limit theorem, saves the day for us. That n is large enough that we can use all the tools anyhow. That's the conditions for the first 3 ones here. Now, in chapter 4, we saw that we could loosen up. Very, very perspective-vising chapter that opens a big world for every one of us, that goes way beyond the actual tools that I share with you within this context. I share tools with you to do 1 and 2 sample statistics based on simulation, instead of basing it on the normal distribution and the analytical t and chi-square distributions. At the same time, we also discussed this error propagation rule, the non-linear error propagation rule with a bit of derivative finding. Usually people find that a bit complicated. That's slightly more mathematical than some of the other things we do. But then we introduced this bootstrapping idea, the simulation idea for doing either error computations like the propagation rule thing, that's where we start, or actual statistical computations, which in a way, in a broad context, is just error propagation of some kind, actually, if you want to say it like that. We do it in two ways, either parametric, where we can assume any distribution for the original data, and put it into the simulation procedure. Hey, if I assume it's a log normal, I just simulate the log normal with the right mean and variance and then see how it goes. Then I do statistics based on simulations, based on the right distribution. Pretty strong tool that you can manage within 2 or 3 lines of R code. Or you would need an entire theoretical statistical class to learn about the math behind that. You don't need it if you understand the concept and you can handle 3 lines of code in R. Then you're up and running. Pretty fantastic. Then a non-parametric bootstrap where we resample the data itself. We don't even assume any distributions. We just reuse the data and do what we call non-parametric based statistics. We create the sampling distribution from the data itself. That's a pretty strong tool also. I show you, if I have to be quite precise, I show you 4 method boxes. The reason why I had the 8 there originally is because originally I distinguished between whether I do it for means that I've been used to in the previous chapters, or I do it for anything else, for instance, the median or a quantile or anything. I can actually easily do it for anything. I call those anythings, I call those theta. Now, in my formulations now, I have talking about thetas primarily in those 4 method boxes, and that could be the mean, or it could be the median, or it could be whatever. So I've given you 4 ways to do statistics here, and that is to do confidence intervals. Whether you want to do it 1 sample or 2 sample comparison with a difference comparison, it's not the only way, but that's what I shared with you. And then whether you do it parametrically based on some distribution or you do it non-parametrically based on the data. You need to know about these tools, right? That was the second part.